Good morning students and a very warm welcome to fourth lecture of the course MA 101 Calculus and ODE. In today's lecture we will discuss about section 8.5 Comparison Tests for Series of Non-Negative Terms from the book Calculus and Analytic Geometry by Thomas and Finney. And in this section we will cover the direct comparison test and the limit comparison test. Now you remember that in last section, that is section 8.4, we introduced the integral test, and while introducing in that section we said that from now onwards we will be considering the series of non-negative terms. Why we did that? We addressed this issue that if you have a series of non-negative terms, then its partial sums will form a non-decreasing sequence, and if that is bounded from above, then we can conclude the convergence, right? So this was the question: given a series of non-negative terms, does the series converge? And this was the corollary to the non-decreasing theorem, which says that a series of non-negative terms converges if and only if its partial sums are bounded from above. So to prove the convergence, we just had to check that if its partial sums are bounded from above or not. So now the question is how to determine whether the partial sums are bounded from above or not. Last time we said that to test the convergence, we just need to check that the partial sums should be bounded from above. Now the question is, how do you test the boundedness of partial sums? So the idea is, sometimes we can establish this by showing each Sn is less than or equal to the corresponding Sn of some series whose convergence is already known to us. Now we are talking about convergence of this series. Suppose you have another series, this one, whose partial sum we are representing by Sn1, and we know that this series is convergent, so we can establish the convergence of this series. How we do that? Let's see with an example. Consider this example. So summation 1 by n factorial, where n varies from 0 to infinity. So this is 1 plus 1 by 1 factorial plus 1 by 2 factorial. Keep on going like this. Now each term of this series is less than or equal to the corresponding terms of this series. How? 1 is equals to 1, 1 by 1 factorial is equals to 1, 1 by 2 factorial is equals to 1 by 2, 1 by 3 factorial, that is 1 by 6, is less than equals to 1 by 4. So we can say that each term of this series is less than equals to the corresponding term of this series, and we know that this series, the series 2, is convergent. Why? Because this is a geometric series. This is an infinite geometric series whose sum will be a upon 1 minus r, and adding 1 to it, it will remain convergent, right? Now how can we conclude the convergence of this series? We said that this is one series in hand, this is another series in hand. We want to test the convergence of this series. We are saying that each term of this series is less than equals to the corresponding terms of the other series, and the other series is known to be convergent. Then how can you conclude the convergence of this series? That is the question. To see how this relation leads to an upper bound of the partial sums, we want to conclude from this result that the partial sums of this series are bounded from above. If they are bounded from above, then the corollary to the non-decreasing theorem will conclude the convergence. Now see, the nth partial sum of the series at hand is 1 plus 1 by 1 factorial plus 1 by 2 factorial plus up to so on 1 by n factorial. Now since each an is less than equals to bn, so this nth partial sum will be less than equal to the corresponding nth partial sum of this series. So this is 1 is less than equals to 1, 1 by 1 factorial is less than equals to 1, 1 by n factorial is less than equal to 1 by 2 to the power n minus 1. So this is from this series. Now this is the sum of finite terms of this series. This will obviously be strictly less than the sum of the infinite series where n varies from 0 to infinity, right? Here n was going from 1 to n minus 1, but now we are saying this is strictly less than 1 plus summation n going from 0 to infinity, and this sum is equals to this number 3. Now Sn is less than equals to this number, which is strictly less than 3, so we can say that Sn is bounded from above by 3. So the partial sums of this series are bounded from above, and hence the given series converges, right? So we have concluded the convergence of this series by comparing it with the terms of the other series whose convergence is already known to us, right? So let's put all this thing in the form of a result. So we established the convergence in last example by comparing the terms of the given series with the terms of a series known to converge. We can test the convergence of many series by comparing their terms to those of the series whose convergence is already known. So this idea can be pursued further to yield a number of tests called comparison tests. Why we are calling them comparison tests? Because we are comparing their terms with the terms of the other series to test the convergence. So here I am saying that we are comparing their terms. We may not be comparing their terms only. There are other comparison tests also called limit comparison tests. So we'll have two types of tests: direct comparison test and limit comparison test. So let's see what is direct comparison test for series of non-negative terms. Let summation an be a series with no negative terms. So we are assuming that an is greater than equals to 0 for all n. The first part of the direct comparison test says that summation an converges if there is a convergent series Cn with an less than equals to Cn for all n greater than n for some integer n. So we are saying that we have this series and we have this series. We want to conclude the convergence of this series. We are saying that it is known that this series is convergent and the terms of this series are a1 plus a2 plus up to so on, and this one are c1 plus c2 plus up to so on, and it is also known that an is less than equals to Cn after a stage. We are not saying a1 is less than equals to c1, a2 is less than equal to c2. No, we are saying that an is less than equals to Cn for some n greater than capital N. Means there exists an integer n over here. That n could be 1. If that n is equals to 1, then we say that a2 is less than equals to c2, a3 is less than equal to c3. Means we can compare the terms of the series after a stage, right? Means there must be some comparison in the tails of the series. Okay, so we said that if an is less than equals to Cn after a stage, and if this series summation Cn converges, then this series summation an, this also converges. This is the first direct comparison test, that this converges if there is a convergent series summation Cn with an less than equal to Cn for all n greater than capital N for some integer capital N. Right? Next part is for divergence. Here it says that this series summation an diverges if there is a divergent series of non-negative terms summation dn with an greater than equals to dn for all n greater than n. So here also we have this series a1 plus a2 plus up to so on, and here we have this series d1 plus d2 plus d3 up to so on. And we know that an is greater than equals to dn after a stage, suppose after this one. So we know that a3 is greater than d3, a4 is greater than d4 likewise. And we also know that this series summation dn, this diverges. Now this series diverges and each term of this series is greater than equal to the corresponding term of this series after a stage, then we can conclude that divergence of this series, that this series also diverges, right? So this uh, part B gives you the divergence of the series, right? So we'll see how to use this direct comparison test. So let's see with an example. Now first we see the list of series whose convergence or divergence is known to us so that we can apply them in the direct comparison test, because when you want to compare the terms of one series with the terms of the other series, then the other series, the behavior of that series should be known to you, right? So all the geometric series with common ratio mod of r less than 1, they are convergent. The telescoping series, we have proved this to be convergence in last lecture. The series summation n going from 0 to infinity 1 by n factorial, we just proved it to be convergent. The p series summation n going from 1 to infinity 1 by n to the power p, where p is greater than 1, this is convergent. And the well-known divergent series are geometric series with mod of r greater than equals to 1, this is divergent. The harmonic series summation n going from 1 to infinity 1 by n, this is divergent, this also we proved. Any series summation an for which limit n tending to infinity an either does not exist or it is different from 0, this is nth term test for divergence. This is nth term test for divergence. And you remember that this test can help us to conclude only the divergence, right? If this limit n tending to infinity an turns out to be 0, then we cannot conclude anything, right? So for any series, if limit n tending to infinity an either does not exist or it is different from 0, we can conclude the divergence of the series. And the p series test, that summation n going from 1 to infinity 1 by n raised to the power p with p less than equals to 1, this series diverges. Let's see with an example how the direct comparison test works. Does the following series converge? Summation n going from 1 to infinity 5 upon 5n minus 1. So the nth term of this series is 5 upon 5n minus 1, which can be written as 1 upon n minus 1 by 5. So basically this is our an. And you see that this is always be greater than 1 by n. So call this as a bn. So an is greater than equal to bn for all values of n going from 1 to infinity, and we know that summation, call this as dn, and we know that summation dn diverges by p series test, right? Now using the direct comparison test, an is greater than dn for all n and summation dn diverges, it means that this series summation an, this also diverges by the direct comparison test. So you have to state the result properly, that an is greater than or equal to dn for all value of n and summation dn diverges. So the given series diverges by the direct comparison test. Next example, does the following series converge? Summation n going from 1 to infinity n plus 2 to the power n upon n square into 2 to the power n. So the nth term of the series can be written as n upon n square into 2 to the power n plus 2 to the power n upon n square into 2 to the power n. So the first term is 1 upon n into 2 to the power n, and the second term here is 1 upon n square. Now this is the nth term of the given series. Now we know that n into 2 to the power n is always greater than equal to 2 to the power n for all values of n going from 1 to infinity. It means 1 upon n into 2 to the power n is less than equal to 1 by 2 to the power n. So that's why we say that 1 by n to the n into 2 to the power n is less than equal to 1 by 2 to the power n, and this is as such 1 by n square. Now what we have, this is the nth term of the series in hand. This is the nth term of the series with which we are comparing the given series, call this as Cn. N varies from 1 to infinity, and you observe that an is less than equal to Cn for all n, and we also know that this series summation Cn converges. Why? Because if you have, when you have this series, this is geometric series with common ratio 1 by 2, and this is a P series which converges because P is greater than 1. And sum of two convergent series is again a convergent series. So we conclude the convergence of this series summation Cn, and by direct comparison test we conclude the convergence of this series given summation An. Right? See next example. Does the following series converge? Now you look at the series that after this stage there is a trend. This is 1 by k factorial. But these four terms are not fitting into this trend. Right? So it's like these four terms, and after that you have a general term for the nth term of the series. Right? So for now we'll just ignore these four terms. Why we are ignoring that? Because if it depends, the behavior of the series depends upon the tail of the series. Right? If this tail converges, then adding four terms to that will not change the behavior of the series. If this diverges, again adding four terms to divergent series, that will also not change the behavior of the series, right? So we will look for the behavior of this series, the truncated series, out of which we are just truncating these four terms for now, and then we can add them correspondingly. Okay, to see this, we ignore the first four terms and compare the remaining terms of the series with those of a convergent geometric series. Now, what is the nth term? For now, it is the nth term is, if you are considering this as your series, summation An, then this series is summation n going from, suppose 1 to infinity, then it is 1 upon n plus 1 factorial. Right? When n is 1, this is 1 by 2 factorial. When n is 2, 1 by 3 factorial, and likewise. And compare this with this geometric series, which is summation Cn, where Cn is 1 by 2 to the power n, where n varies from 1 to infinity. Keep the indices same. Okay. Now you see 1 by 2 is equals to 1 by 2, that is the first term of this series is equal to the first term of this series. And about the second term of the series, second term of this series is, when you substitute n is equal to 2, you have 1 by 3 factorial. So this is the second term of this series. And the second term of this series is 1 by 2 square. So 1 by 3 factorial is less than 1 by 2 square, right? Likewise, the next term is 1 by 4 factorial, which is less than 1 by 8. So we have this sum, this summation an, this is less than equal to this summation cn, right? So now you state the test properly. Observe that an is less than equals to cn for all n, and it is also known that summation cn converges being a geometric series with common ratio r 1 by 2, which is less than 1, right? So observe that an is less than equals to cn for all n, and summation cn converges. Hence we can say that summation an converges. Now summation an is a truncated series, right? So the truncated series converges by the direct comparison test, and hence the original series also converges, because adding 4 terms to a convergent series won't change the behavior of that series, right? So we conclude that the series under consideration is convergent. Next type of test is the limit comparison test. Till now, we were directly comparing the terms of one series with the terms of another series whose behavior is already known to us. Now, in the limit comparison test, this test is particularly useful for series in which an is a rational function of n. When an is given by some f of n upon some g of n, and of course this should be not equal to 0 for any value of n, right? When you have functions of this form, then the limit comparison test is useful. Now what is the limit comparison test? Suppose that an is greater than 0 and bn is greater than 0 for all n greater than or equal to n. So you have two series, and we are saying that the nth term of both the series are positive after a stage. Okay. Now the first part, if limit n tending to infinity an upon bn is a number c strictly greater than 0, then this series summation an and this series summation bn both converge or both diverge, right? So if you want to see the behavior of this series summation an, we will think of another series summation bn. We'll check the limit of these two summation an by bn. If this is a number c, suppose 1, it is greater than 0, then these two will behave the same way. Now if this you have chosen your bn, if this is a convergent series, then an will also be convergent. If this is a divergent series, then this an will also be divergent. This is the first part of the limit comparison test. Second part is, if limit n tending to infinity an by bn turns out to be a number 0. If this turns out to be 0 and this series summation bn, this converges, then an will also converge. And the last part of the result is, if limit n tending to infinity an upon bn is infinity and this series diverges, then an will also diverge. So we'll solve a couple of problems for each of these three cases. So let's solve a problem for first part of the limit comparison test. Use the limit comparison test. Using the limit comparison test, which of the following series converge and which diverge? So the first series is given and the nth term of the series is also given. It is 2n plus 1 upon n plus 1 whole square. So just opening the whole square, this is the nth term of the series. say an is equals to this term, the nth term of the given series. Now, how do you choose Bn? Because you have to eventually find the limit n tending to infinity an by Bn. So one way is you see how an behaves for larger values of n. As you keep on increasing your n, how an behaves. So see, as n is getting larger and larger, in the numerator only 2n. This term will play the role. This term will dominate this number 1. Right? Suppose if this n is 1000, then if n is 1 million, then eventually the behavior of the numerator is coming from this term 2n. And likewise in denominator, n square will dominate the other terms. Right? Since the leading terms dominate for large n, we expect an to behave like 2n upon n square. That is 2 upon n. So from this number 2 upon n, we should get an idea that how do you choose our bn so that their ratio will give me a finite number. So we let bn is equals to 1 by n, and we also know that this bn diverges, right? This bn diverges. Now if this limit n tending to infinity an by bn will turn out to be a number c greater than 0, then we can say that summation an and summation bn either both converge or both diverge, and knowing that bn diverges, an should also diverge. Let's see. Limit n tending to infinity an upon bn is equals to limit n tending to infinity, just multiplying this by n. So you have 2n square plus n upon n square plus 2n plus 1, which is equals to 2. Now this is some number c which is greater than 0, and since summation bn diverges, so by part 1 of the limit comparison test, we can say that summation an diverges. Okay, so which way we have to proceed? Given a series, write the nth term of the series. See the behavior of an as n becomes larger and larger, and as n increases, this term 2n and this term n square are going to dominate the rest of the terms. So this an will behave like 2 upon n. Now on the basis of how this term is behaving as n is getting larger and larger, you choose your bn. Choose bn is equals to 1 by n, so that this limit now is a number, finite number 2, which is strictly greater than 0, and hence by limit comparison test, an and bn, series an and series bn, both converges or both diverges. Knowing that summation bn diverges, conclude the divergence of summation an. See next example. Summation n going from 1 to infinity 1 upon 2 to the power n minus 1. So this is the nth term of the series, and we see for larger values of n, this minus 1 is not going to contribute, and the nth term an behaves like 1 upon 2 to the power n. So we suppose that bn is equal to 1 upon 2 to the power n, and we know that this series summation bn, this converges being a geometric series with common ratio 1 by 2. Now check the limit n tending to infinity an by bn. It is equal to limit n tending to infinity an is 1 upon 2 to the power n minus 1 upon 1 upon 2 to the power n. So this is 2 to the power n upon 2 to the power n minus 1. So this is just dividing both these terms by 2 to the power n. So this is 1 upon 1 minus 1 by 2 to the power n. And as n tends to infinity, this term will tend to 0, and the limit is equal to 1. So if the number c, which is greater than 0, and since bn diverges, So by first part of the limit comparison test, we say that summation an also converges. See next example. Nth term of the series is 1 plus n ln n upon n square plus 5, where n varies from 2 to infinity. Okay, so call this as your an. So let an is equals to this one, and for large values of n, the numerator, in the numerator this term will dominate, and in the denominator n square will dominate, and this an behaves like n ln n upon n square, that is ln n upon n, right? So here we will not choose bn is equal to ln n upon n, because we should choose bn in such a way that behavior of this series is known by just looking at the series. This is that simple series, right? So rather than choosing bn is equal to ln n upon n, we will choose it is equal to 1 by n, and we know that this series is a divergent series, right? So choose bn is equal to 1 upon n, and this series diverges by p-series test. Now check the limit n tending to infinity an upon bn. It turns out to be limit n tending to infinity n plus n square ln n upon n square plus 5. Now you just easily compute this limit and it will turn out to be infinity. So this is by part 3 of the limit comparison test, which says that if this limit is infinity and bn diverges, then an will also diverge. Now suppose here you did not get 0, you did not get infinity, and you get some number c, right? Maybe equal to 0 or not equal to 0. Then you won't be able to conclude anything, right? If you get here 0, then this test is inconclusive and you have to choose another bn, right? For now everything is working fine. Whichever bn we are choosing, we are landing up in one of the 3 parts of the limit comparison test, so everything is fine. Now see next example. Does the series summation n going from 1 to infinity ln n whole square upon n cube converge? Now this is the nth term of the series, ln n whole square upon n cube. Now looking at the series, we cannot say as n tends to infinity how the series is behaving, so we will just take some value of bn. Looking that it is there 1 by n cube is there, basically n cube is there in the denominator, so we'll just try with bn is equal to 1 by n cube, and we know that this series by p-series test, this series converges. Now check what is limit n tending to infinity an by bn. Now limit n tending to infinity an by bn is equals to ln n whole square, right? Because this n cube cancels out. Now as n tends to infinity, this will tend to infinity. Now limit n tending to infinity an by bn is infinity and bn converges. So we cannot conclude anything. The result says that if this limit is infinity and if bn diverges, then an diverges. But if this limit is infinity and bn converges, we cannot conclude anything from the limit comparison test. So we will have to take another value of bn so that we can conclude something. Right? Now we took 1 by n cube now, this series, right? We took bn is equal to this one. If you increase this number, if you say now you will take 1 by n to the power 4 or n to the power 5, then what will happen? Limit n tending to infinity, an by bn will turn out to be n times of this one, then it will be n square times of this one. So this will again remain divergent only. This limit will remain infinity only, and this bn will remain convergent. So it's the same scenario. Nothing is going to change, right? we took Bn is equal to 1 by n cube. Now when you have to take another value of Bn, I am saying that no need to go for higher values of, for higher powers of n. Instead, reduce this number 3 to 2 so that we can make some conclusion. That also we have to test whether we are able to make that conclusion or not. Take Bn is equal to 1 by n square. Now again this series also converges by P-series test. Now we have to see this limit, that what is this limit, right? Limit n tending to infinity, an is this term upon Bn is 1 by n square, and just simplifying it we have ln n whole square by n. Now when n tends to infinity, this is infinity by infinity form, so use L'Hopital's rule, right? So derivative of this one with respect to n, so this is 2 ln n into derivative of ln n is 1 by n, and derivative of n here is 1. So you have 2 times limit n tending to infinity ln n upon n, and this is a standard limit that this limit is equals to 0. So 2 times 0 is 0. If you do not remember this limit, then you can just again say it is infinity by infinity form, and again using L'Hopital's rule, derivative of 1 ln n is 1 by n and derivative of n is 1. And now when you take n tending to infinity, this will be equal to 0, right? Now see what happens. This limit turns out to be a number 0 and Bn converges. So this fits into the second part of the limit comparison test, which says that if this limit is 0 and Bn converges, then An converges, right? So we conclude that this series converges. So you have to do the problems 1 to 40 from exercise 8.5 from the book Calculus and Analytic Geometry by Thomas and Finney. And that's about it. Have a nice day.